We are looking at section 5.3 bond energies and something called enthalpy. So enthalpy, which is delta H, is a measure of the total internal energy of a substance. So during a chemical reaction, the bonds and the reactants must first break. And for bonds to be broken, energy must be added, which is in fact an endothermic process. Don't think too much about this here. I'm just saying that that's what's happening. This results in the energy term having a positive sign. Okay, that's going to be an important part here. So endothermic you can think of as being positive. That's an arrow. Making new bonds releases energy, which is an exothermic process. Thus, the energy term associated with this is negative. So endothermic is negative. Again, let's keep that in our minds for later. So what we're talking about here is delta H is equal to the sum of the energy required to break the old bonds, which are positive values, and we are going to in fact subtract the sum of the energy released in the formation of the new bonds, which are going to be negative values. It's really kind of a moot point here. Really all we're doing is we are taking our energy from our reactant side and subtracting the energy from the product side. So reactants minus products. It's kind of our mantra for this. Now this table is what we're going to be referring to come up with some bond energy values. This is included back on the home page. You can click on that. So we have a couple columns here. We've got a bond column, and we also have an energy column. Notice the energy column is in kilojoules per mole. Then our columns just repeat. So it's a repetition here. It's really just like one giant table. And so we really, and it doesn't matter if you're talking about later question whether it's an HC bond or a CH bond. So all we're going to do is we're going to find it, and then we're going to need the number that associates with it. These energy values are going to help us evaluate if something's endothermic or exothermic. So make sure you have this table printed out or handy when you go to do your homework questions. So now we're going to proceed with a question. Our first one we're going to do is we're going to prove that the combustion of pentane is exothermic. Anytime you burn something, combustion, it has to be an exothermic answer. So we're just proving it. So what we need to know is, well, sort of our general combustion equation, if you're not familiar with it, is a fuel, which is going to be our hydrocarbon, which is in this case is going to be pentane, plus oxygen gas. Always yields water vapor, carbon dioxide, and energy. So that is the exothermic energy term we are going to go and set about to numerically prove. So instead of writing fuel here, let's sub in our formula for pentane, C5H12, and now we're going to have to balance this one. And so there we go. I just jumped ahead and balanced that for you. So once you have that equation balanced, and the balanced numbers are important, we can't do this properly without them, we're going to have to draw all the molecules. So there is pentane, and oxygen has a double bond, and there are 8 of them. And we've got 6 waters here, and we have 5 carbon dioxides with the double bonds. And I've removed the energy at this point because we know that's what it's going to be. Okay, so there's that same equation rewritten. Now, the question I have is how many different types of bonds are present in each molecule? So looking at this one here, if you identify how many different types of bonds, you'd say, well, there's 2. We've got carbon-carbon bonds. Yeah, there's more than one of them, but here's a carbon-carbon bond. And additionally, we have a carbon-hydrogen bond, and there's a bunch of those. So there's 2 types of bonds here. Here, there's only one type. It's an oxygen double bond. Here, there's only one type. It's an OH. And here, there's only one type. It's a CO double bond. Sure, there are multiple ones here, but we'll consider that as we proceed. So back to our first molecule, pentane here, I have counted 4 carbon single bonds. 1, 2, 3, 4. So there are 4. I have counted 12 carbon hydrogen bonds, and that covers all the bonds in the first molecule. Now on to the oxygen double bonds. There's nothing really to change there. There's 8 oxygen double bonds. Now over to this side, we need to be careful. So let's consider our water molecule. We have 2 OH molecules, 2 OH bonds per molecule, right? There are 2 green lines I drew there. 2 times 6. So there are in fact 12 OH single bonds in this molecule. And the same thing applies over here. we've got a couple of oxygen-carbon double bonds, 2 per molecule, 5 molecules. That makes 10. Okay, so now is where we get out this table here and we start to look up the different values and just simply substitute them in. So a carbon-carbon bond is worth 347. There's 4 of them. A carbon-hydrogen is 338. We've got 498 for the oxygen double bond and 460 for the OH bond and 745. So once you have all those numbers, I like to do kind of a left side, right side total. So you should get 4928, double check the math there, and we get 1297. So what we're going to do is now we are going to simply subtract our energy required and take away our energy released. So subtract the numbers just as they appear. There we go. And notice we get a negative value. Negative value is perfectly good. So negative value is going to indicate that energy has been given off into the system. So it gets hot. So it's leaving the system, my mistake, it goes into the surroundings. So this negative value indicates energy being released into the surroundings. So we know this is exothermic, but I just thought I would show you this one more time. So there's our reactant kilojoule per mole starting values. The bonds break and the bonds reform, and it took 12,970 kilojoules per mole. And you'll notice that we have a negative, like it's gone down, right? It's gone down by our particular answer right here. So yeah, and that's a good representation. So when we go to write our final equation, there's our equation, and with a negative value, we're going to put it on the right side. And that question is done. That's exothermic. So let's try another question here. Let's determine if the decomposition of water is exo or endothermic. So firstly, we'll have to come up with an equation. So I've taken the liberty of already coming up with it. So now we need to dissect our molecule. I like to kind of draw this one out here. So really, that's what our waters are going to look like. And that's what our hydrogen and our oxygen gas will look like, single and double bonds. Now it's a matter of, I think I'm going to break this down a little bit further because we have 2 OH bonds per molecule, and there are 2 molecules in total. So that's going to give us 4 of those. The rest kind of stays unchanged. There's nothing to simplify there. Our next step is we're going to start to plug in the values from our table. And there we go. You can double check my math. And those are the values you should find. And when we subtract, this time we end up with a positive value. And so endothermic, and again, even looking from this step, you can see that the number is bigger on the left side, okay, and it's bigger by 470. So that means it's an endothermic reaction. We need this much energy to actually drive this reaction to start it off. So you can see our values as they fill in there. There's our change in energy. So once again, we can write our equation, and this time we're going to put the value out front. And there is your endothermic example.